Good afternoon. During one of the past lectures, I introduced the notion of a first fundamental form. Today we will see how to express the first fundamental form in local coordinates. So, I want to start by recalling the definition of first fundamental form. So, if S is a regular surface, and P is a point of S, then the first fundamental form, I will write for short FFF, is a map defined on TPS with values in R given by this assignment, where this notation means the restriction to TPS, to vectors of TPS of the square norm function. In order to express the first fundamental form in local coordinates, we need to consider a surface patch sigma and we define three new functions. E, F, G on U with values in R, such that for all Q in U, where U is exactly this open set here, we have that E at Q is the square norm of sigma UQ F of Q is the inner product of sigma UQ sigma VQ and G of Q is the square norm of sigma VQ, and as before, the index P means that we are considering the restriction of the square norm function and of the inner product to vectors of TPS. And of course here P is sigma Q. Now let's see what is the relationship between E, F, and G and with lengths, angles, and areas. We have seen that, we introduced in the past the notion of intrinsic measurement. A measurement is intrinsic if it depends only on the first fundamental form. So now we want to express this fact in terms of E, F, and G. So we have the lemma 3.77, which says that if X and Y are elements of R2, then the inner product d sigma Q evaluated at X, d sigma QY, this can be expressed not only as A sigma UQ plus B sigma VQ multiplied by C sigma UQ plus D sigma VQ, but also using E, F, and G. As follows: AC times EQ plus AD plus PC F of Q plus BD times G of Q. The second statement, so this was the first one. Second statement says that if X is equal to AB in R2, then we have that the square norm of D sigma Q X P squared is A square E Q plus 2 A B F of Q plus B square G of Q. Clearly, the statement 2 is an easy consequence of statement 1. Just take X equal to Y. The third one, if gamma is a curve is a regular curve in U with component functions u of t, v of t. So this means that gamma t can be written as this pair of functions. Then we have that the arc length of sigma composed with gamma, since gamma is a curve in U and sigma is a surface patch for S, then sigma composed with gamma is a curve on the surface. This is the integral from 0 to L of the square root of u prime t squared e gamma t plus 2 u prime t v prime t f of gamma t plus v prime t squared g of gamma t dt. If you want to prove 3, just use 2, and remember that the arc length of sigma composed with gamma, according to the definition, is the integral from 0 to L of the length of sigma composed with gamma prime dt but if you use the chain rule, what is sigma composed with gamma prime? It is just d sigma along gamma t applied to gamma prime t. So this means that if you want to prove this formula, just use 2 with x equal gamma prime of t and q equal gamma t. The last statement, let's write here. For if R contained in V is a polygonal region, then the area of R is the integral, the double integral over sigma inverse of R of the square root of E g minus f squared dA. If you want to prove this formula, just use the fact that by definition the area of R, this is the double integral over sigma inverse of R of the length distortion of this sigma dA and you use the identity which says that the length distortion of this sigma, this is the length of the cross product sigma u times sigma v, and using the properties of the cross product, this can be written as the square root of sigma u squared, sorry, the square length of sigma u times square length of sigma v minus sigma u inner product sigma v. But do you remember what is the definition of E, G, and F? E is exactly this function, G is exactly this function, and this is exactly F. I forgot a square here, sorry. So this is the square root of E, G minus F squared. It remains to prove statement 1. So proof of 1, we proved all the others. This follows from the fact that you can write x as a e1 plus b e2, y as c1 plus d e2, and you use the fact that d sigma q of x is then equal to d sigma q at a e1 plus b e2. This is equal to a d sigma q e1 plus b d sigma q e2. But what is the derivative of sigma in the direction e1 is a sigma u at q and multiplied by the a, and for the same reason, the derivative of sigma in the direction given by E2 is sigma VQ to be multiplied by B. A similar result is equal holds true for D sigma QY. So D sigma QY it is equal to C sigma U Q plus D sigma VQ, and you get immediately the inequality, sorry, the identity D sigma QX D sigma QY equal to this. And then using bilinearity and symmetry of the inner product, you can prove immediately, almost immediately. Sorry, I had to write here this symbol and not a bracket, you can prove immediately that this is equal to AC EQ plus AD plus BC F of Q plus BD G of Q. Okay, we are ready now to give another definition. Definition 3.78, which says that the first fundamental form in the local coordinates UV, also known as first fundamental form of sigma, is the expression F1 equal to E du squared plus 2F du dv plus G dv squared. Where what is the meaning of du and dv? Du denotes the derivative of the function defined on U. Remember that U is the open set on which is defined sigma, the surface patch we are using. That maps UV into U. Similarly, dV denotes the derivative of the function on U defined by UV is sent to V. So if X is a vector of components AB, then du q of X is A, and dv q of X is B. Why this is true? Of course, for every q in u. Why this is true? Because you write as before a x equal ab equal a e1 plus b e2. Then what is duq of x? This is duq of a1 plus b2. Then this is a duq e1 plus b duq e2. And it is immediate to see that the derivative of u in the direction e1 is equal to 1. Why? Because we are looking at this map here. We look at changes of this function along the direction e1, and the derivative is exactly equal to 1. Instead, this derivative here is 0, and the result is a. Similar computation for proving that dvqx is b. So as a conclusion, what is a consequence of these two formulas is that f1 evaluated at x this is nothing but then d sigma q x squared for all q in u and the x in t q u equal to r2. If you want to check that this formula is true, just write as I did before, x equal to a b equal a e1 b e2, and expand the formula for f1, and you will see that this coincides with d sigma qx. Now let's see some examples. The first one is the first fundamental form for a surface patch of the sphere. So consider the surface patch sigma defined on 0 to pi times 0 pi defined by sigma of theta phi equal sinus of phi cosinus of theta, sinus of phi sinus of theta, cosinus of phi. Then what is E? E is a sigma theta square. This is the length of the vector minus sinus of phi sinus of theta, sinus of phi cosinus of theta, 0, and this is equal to sinus square of phi. F is the inner product of sigma theta sigma phi, and you can prove it to be equal to 0 because this is the inner product of minus sinus of phi sinus of theta, sinus of phi cosinus of theta, 0, multiplied by cosinus of phi cosinus of theta, cosinus of phi sinus of theta minus sinus of phi. And this is 0. It remains to compute G. G is the square of the length of sigma phi, that is the length, the square of the length of this vector. Sorry, I made a typo. This is theta, and this is minus sinus of pi. And it is equal to 1. So the first fundamental form F1 takes the form sinus square phi d theta square plus d phi square. And what are the consequences of this formula? If you have a curve on S2 given by sigma evaluated at theta t phi of t with t in 0 L, then the arc length this is given by the integral from 0 to L of the square root of sinus square of phi of t theta prime t square plus phi prime t square dt. Why? Because this is E evaluated at gamma t, and G evaluated along gamma t is 1, and F is 0. What about the area? So if R is contained in S2 and is a polygonal region. Actually, we should be more precise. The surface patch I'm using covers S2 minus an arc. So if you want to be precise, we should write R containing S2 minus that arc, which is a set of measure 0. So the area will be given by the integral over sigma inverse R or the square root of EG minus F squared dA, which in this case reduces to the integral over sigma inverse R of sinus of phi dA, because this is 0, this is 1, and this is sinus square of phi. And this is a formula we already knew, because you can compute the area of R using the definition, the one involving the area distortion. Second example, the first fundamental form for a graph. So if U containing R2 is open, and F defined on U with values in R is smooth, then let's use another notation, because G is something else. Let's use gamma for the graph. Let's write also x, u, x, y, and u. This is the graph of f, and this is a regular surface. And you know that it can be covered by a single surface patch given by x, y, f of x, y. So what is the first fundamental form for this surface patch? In order to answer this question, we need sigma x at q, which is given by 1, 0, f of x at q, and sigma y at q, this is 0, 1, fyq, where q is an arbitrary point of U. So the first fundamental form f1, this is 1 plus fx squared dx squared plus 2 fx fy dx dy plus 1 plus f1 square fy squared dy squared. Okay, the next topic of today is the Gauss map. Our next goal is to introduce the notion of curvature of a surface. The first tool I need is the Gauss map. How to define this object? So let S be an oriented surface and let N denote the orientation. So this means that we have a vector field on S. For each point of S, this map gives us a vector of length 1. Okay, since N of P has a length 1 for every P in S, we can think of this map as a map from S with values in S2. And this map here is called Gauss map. Now let's look at the derivative of this map. Fix P on S, then the derivative of this function at P, you know very well it is a function on TPS and it takes value on T and not P S2. Now let's observe what follows. The vector N of P is orthogonal to TPS. Why? Because by definition N is a vector which is orthogonal to the surface. This means that it is orthogonal to any vector in TPS. But what about T and PS2? So if this is the surface, let's make a picture. If this is the surface, and this is S2, suppose that this is n at p, then the Gauss map is a map which associates to the point P the vector of S2 that you get taking this vector here and drawing it such that its tail is the origin and its tip is on S2. So for example, you get this thing. Now it is clear that N of P is also orthogonal to Tn of P S2. Why? Just observe the picture. If you think of Tn of P S2 as a plane, tangent to S2 at the point given by the tip of N of P, then it's clear that N of P is orthogonal to any vectors in Tn of PS2. This implies that TPS can be identified with Tn of P S2. And we can think of them as the same space over subspace over 3. The next tool I need is the Weingarten map, and this is defined as it is denoted by WP, and it is defined as minus the derivative of n at p. So WP is a map from TPS into TPS after the identification of TNPS2 with TPS. And once we have WP, we can define the Gauss curvature of S at P as the determinant of the matrix which represents WP, and we can define the mean curvature of S at P as 1/2 trace of the same matrix. So if you want to write this using symbols, you have that K of P, Gauss curvature, is a determinant of WP, and H of P, mean curvature, this is 1/2 trace of WP. The reason why there is a minus here will be clear later. For the moment, let's try to give, let's try to see what is the geometric meaning of the Weingarten map. So we said that WP is defined as minus D and P. Now suppose that V is a vector in TPS. How to compute WP of V that is minus dn P at V? You know how to answer to this question. Use proposition 3.7. It's a proposition which says that if you have to compute derivative of a function along a given direction, you have to take a curve gamma such that the initial point is a point where you want to compute the derivative, and this initial velocity is the vector along which you are computing the derivative. Then the derivative of n in the direction of v is n composite gamma prime at 0. We can use another notation to find n of t as n composite gamma t. This implies that d and pv is n prime at 0, and consequently w p at v is this. So essentially we can say that the minus WPV equal n prime 0 is the speed and direction in which n tilts if okay, it's right as I pass P. So some of you could ask me the following question. In order to define the Weingarten map, we have chosen an orientation n for the oriented surface S. What happens to WP, KP, and HP if we replace n by minus n? Okay, clearly, since WP is minus dNP, if we change n with the minus n, then the value of WP is replaced by minus WP. Simply because we are changing the sign of the function of which we are computing the derivative. And instead, K of P doesn't change. K of P does not change. Why? Because all the entries of the matrix representing WP change sign, but the determinant of this matrix does not change because the matrix is a square matrix of order 2. Instead, the mean curvature changes its sign why? Because the entries of the matrix change their sign. So this means that the trace of the matrix changed its sign. So the conclusion is that only the Gauss curvature K is independent of the choice of the orientation of S. And this means that it is possible to define it also for non-oriented surfaces. Now let's see three examples. The first one is the plane. So it is clear that a plane, it can be oriented choosing a constant unit normal field n. So for example, if you have this plane here, you can choose n to be the vector, the constant vector field, which assigns to each point of the plane this vector. So this means that the derivative of this function for any p is 0. And this means that the WP is 0, and this implies that the Gauss curvature is 0 and the mean curvature is 0. Second example is a sphere. So let's start this time writing what is a sphere of radius r. I will use this notation. This is a set of points in R3 such that their position vector has length r. Let's choose an orientation for S2R. So an orientation for S2R is given by NP equal to P over length of P. In other terms, you take the position vector of each point and you divide it by its length. So in other terms, you can write P over R. This points outward pointing it's clear why. Because if this is S2R this is P, then you can get NOP dividing P by its length. So if gamma, okay, we want to compute WP at V, where V is a vector of TP S2R. How we do this? We consider a curve, gamma. Of course, it must be regular. So let me write a regular curve. Such that gamma 0 is P, gamma prime 0 is equal to V. Then WPV is minus N prime 0, that is minus ddt n of gamma t at t equals 0. But what is n of gamma t? N of gamma t is nothing but then gamma t over r. If you want to be more precise, you can write like this. This is true because gamma t is a curve in S2R, so the length of the position vector at time t for any t is r. So this implies that ddt of n gamma t at t equal to 0, this is the derivative of gamma t over r at t equals 0. R is a constant, and this is equal to V over R. Why? Because we know that gamma prime 0 is V. So this implies that WP V is minus V over R. So WP, the matrix which represents WP with respect to any basis is given by minus 1 over r, 0, 0, minus 1 over r. So this implies that the mean curvature is 1 over r squared, and the Gauss curvature is 1 over r squared, and the mean curvature is minus 1 over r. For any in S2R. Next example is more complicated from the computational point of view, and it's about the Weingarten map of a graph with a critical point. So let's write Weingarten map at a critical point of a graph. So let's consider a graph of a function where f is a smooth function defined on the open set U with values in R. You know that the graph can be covered by a single surface patch sigma given by x, y, f of x, y. And we already computed sigma x. This is 1, 0, f of x. Sigma y, this is 0, 1, f of y. And we can orient gamma with n given by sigma x times sigma y over its length. And this is given by fx squared, minus fx minus fy 1 divided by its length. Now we want to compute WP where P equals sigma q, assuming that Q is a critical point for F. This means that if Q is x0, y0, then fx x0, y0 equal f of y x0, y0 equals 0. If this is true, we have that n at P is just 0, 0, 1 because f of x and f of y are 0. and sigma x is 1, 0, 0 equal E1, sigma y is 0, 1, 0 equal E2, and this says that Tp gamma is a span of E1, E2. Okay, we want to compute WP, so we have to consider a basis of Tp gamma is on the blackboard. So we need to compute WP E1 and WP E2. We know how to do this. We consider a regular curve on gamma such that gamma 0 is P, gamma prime 0 is E1. So for example, gamma equal x0 plus t, y0, f of x0 plus t, y0. This is a curve on gamma. How I got it? I composed sigma with a curve given by this map. So we have that WP E1 is minus, and let's write 1, 0, where n1t is n composed with gamma t. So this means that I have to evaluate this function along this curve, and this is minus f of x, x0 plus t, y0, minus f of y, x0 plus t, y0, 1, divided by f of x square x0 plus t, y0 plus f of y square x0 plus t, y0 plus 1. Okay, if you make computation, you will find that n1 prime 0, this is just minus fxx evaluated at this point, minus fyx evaluated at the same point, 0, and WPE1 will be minus n1 prime 0. I don't write what is WPE1, it's immediate to get it. You do the same for finding WPE2. This is minus N2 prime 0, where N2T is N evaluated at gamma, let's write tilde T, where gamma tilde T is given by x0, y0 plus T, f of x0, y0 plus T. This is a curve with gamma tilde 0 is equal to P, gamma tilde prime 0 is equal to E2. And if you make this computation, you will find that N2 prime 0 is equal to minus fxy x0 y0 fyy x0 y0 0. And this means that the WPE1, this is a negative N1 prime 0, which is here. So this can be written as fxx x0 y0 E1 plus fyx x0 y0 E2, and WPE2 is N2 prime 0 after a change of sign. So it is given by fxy x0 y0 E1 plus fyy x0 y0 E2. So this means that the matrix representing WP is fxx x0 y0 fyx x0 y0 fxy x0 y0 fyy x0 y0. Here I am using, of course, the basis E1, E2 for TP gamma. What is now the Gauss curvature? This is the determinant of WP, and this is given by fxx x0 y0 fyy x0 y0 minus fxy x0 y0 squared So remember now what you studied in your course of Calculus 2. You have that you can use the second derivative test for determining the nature of the critical point. You have that if this quantity is positive, then you have a local minimum or maximum. Instead, if this quantity, which is the curvature, the Gauss curvature, is negative, you have a saddle point. I think it's a good point for ending this lecture. So that's all for today. Thank you for your attention.